Hello everyone. Today we're going to learn the first lesson of physics. Physical world. Why the lesson is for us. Okay. This lesson gives us the basic knowledge of why physics, scope of physics, basic laws of physics. Let's start. Science and its origin. Science is a systematic understanding of natural phenomena in detail so that it can be predicted, controlled, and modified. Science involves exploring, experimenting, and speculating phenomena happening around us. The word science is derived from a Latin verb scientia meaning to know. Scientific method is a way to gain knowledge in a systematic and in-depth way. It involves systematic observations, controlled experiments, qualitative and quantitative reasoning, mathematical modeling, prediction and verification, or falsification, of theories, speculation or prediction. Science does not have any final theory. The improved observations, accurate tools keep improving the knowledge and perspective. Johannes Kepler used Tycho Brahe's research on planetary motion to improve Nicholas Copernicus' theory. Quantum mechanics was developed to deal with atomic and nuclear phenomena. Work of Ernest Rutherford on nuclear model of atom became basis of quantum theory given by Niels Bohr. Antiparticle theory of Paul Dirac led to the discovery of anti-electron, positron, by Carl Anderson. Natural sciences. Natural science is a branch of science concerned with the description, prediction, and understanding of natural phenomena, based on observational and empirical evidence. It consists of following disciplines: physics, chemistry, biology. Physics. Physics is a study of basic laws of nature and their manifestation in different natural phenomena. Physics is the study of physical world and matter and its motion through space and time, along with related concepts, such as energy and force. Word physics is derived from a Greek word physique meaning nature. Two principal types of approaches in physics are: 1. Unification. This approach considers all of the world's phenomena as a collection of universal laws in different domains and conditions. Example: law of gravitation applies both to a falling apple from a tree as well as motion of planets around the sun. Electromagnetism laws govern all electric and magnetic phenomena. 2. Reduction. This approach is to derive properties of complex systems from the properties and interaction of its constituent parts. Example: temperature studied under thermodynamics is also related to average kinetic energy of molecules in a system, kinetic theory. Impact and uses of physics. It can explain a phenomena happening over a large magnitude with a simple theory. Experiments and observations are used to develop new theories for unidentified phenomena and improved theories for existing phenomena. Development of devices using laws of physics. Scope of physics. Scope of physics is vast as it covers quantities with length magnitude as high as 10 power 40 m or more, astronomical studies of universe, and as low as 10 power minus 14 m or less, study of electrons, protons etc. Similarly, the range of time scale goes from 10 power 22s to 10 power 18s and mass from 10 power minus 30 kilograms to 10 power 55 kilograms. Physics is broadly divided into two types based on its scope: classical physics and modern physics. Classical physics deal with the macroscopic phenomena while the modern physics deals with the microscopic phenomena. Macroscopic domain. Macroscopic domain includes phenomena at large scales like laboratory, terrestrial and astronomical. It includes following subjects: mechanics, electrodynamics, optics, thermodynamics. Mechanics, it is based on Newton's laws on motion and the laws of gravitation. It is concerned with motion/equilibrium of particles, rigid and deformable bodies and general system of particles. Examples: propulsion of rocket by ejecting gases, water/sound waves, equilibrium of bent rod under a load. Electrodynamics, it deals with electric and magnetic phenomena associated with charged and magnetic bodies. Examples: motion of a current-carrying conductor in a magnetic field, the response of a circuit to an AC voltage signal, the propagation of radio waves in the ionosphere. Optics, it deals with phenomena involving light. Examples: reflection and refraction of light, dispersion of light through a prism, color exhibited by thin films. Thermodynamics, it deals with systems in macroscopic equilibrium and changes in internal energy, temperature, entropy etc. of systems under application of external force or heat. Examples: efficiency of heat engines, direction of physical and chemical process. Microscopic domain. Microscopic domain includes phenomena at minuscule scales like atomic, molecular, and nuclear. It also deals with interaction of probes like electrons, photons, and other elementary particles. Quantum theory has been developed to handle these phenomena. Factors responsible for progress of physics. Quantitative analysis along with qualitative analysis. Application of universal laws in different contexts. Approximation approach, complex phenomena broken down into collection of basic laws. Extracting and focusing on essential features of a phenomenon. Hypothesis, axiom, and models. Hypothesis is a supposition without assuming that it is true. It may not be proved but can be verified through a series of experiments. Axiom is a self-evident truth that it is accepted without controversy or question. Model is a theory proposed to explain observed phenomena. Assumption is the basis of physics, where a number of phenomena can be explained. These assumptions are made from experiments, observation, and a lot of statistical data. Technological applications of physics. Several examples where physics and its concepts have led to discoveries/inventions are listed below. Steam engine was developed from the Industrial Revolution in 18th century. Wireless communication was developed after discovery of laws of electricity and magnetism. Neuron-induced fission of uranium, done by Hahn and Meitner in 1938, led to the formation of nuclear power reactors and nuclear weapons. Conversion of solar, wind, geothermal etc. energy into electricity. Fundamental forces in nature. The forces which we see in our day-to-day life like muscular, friction, forces due to compression and elongation of springs and strings, fluid and gas pressure, electric, magnetic, interatomic and intermolecular. Forces are derived forces as their originations are due to a few fundamental forces in nature. A few fundamental forces are gravitational force, electromagnetic force, strong nuclear force, weak nuclear force, gravitational force. It is the force of mutual attraction between any two objects by virtue of their masses. It is a universal force as every object experiences this force due to every other object in the universe. Electromagnetic force, it is the force between charged particles. Charges at rest have electric attraction, between unlike charges, and repulsion, between like charges. Charges in motion produce magnetic force. Together they are called electromagnetic force. Strong nuclear force, it is the attractive force between protons and neutrons in a nucleus. It is charge independent and acts equally between a proton, a neutron, and a neutron, and a proton, and a neutron. Recent discoveries show that protons and neutrons are built of elementary particles, quarks. Weak nuclear force, This force appears only in certain nuclear processes such as the beta decay of a nucleus. In beta decay, the nucleus emits an electron and an unchanged charged particle called neutrino. This particle was first predicted by Wolfgang Pauli in 1931. Below table shows difference between the above forces. Conserved quantities. Physics gives laws to summarize the investigations and observations of the phenomena occurring in the universe. Physical quantities that remain constant with time are called conserved quantities. Example, for a body. Under external force, the kinetic and potential energy change over time, but the total mechanical energy, kinetic plus potential, remains constant. Conserved quantities can be scalar, energy, or vector, total linear momentum and total angular momentum. Conservation laws. A conservation law is a hypothesis based on observation and experiments which cannot be proved. These can be verified via experiments. Law of conservation of energy. According to the general law of conservation of energy, the energies remain constant over time and convert from one form to another. The law of conservation of energy applies to the whole universe, and it is believed that the total energy of the universe remains unchanged. Under identical conditions, the nature produces symmetric results at different time. Law of conservation of mass. This is a principle used in analysis of chemical reactions. A chemical reaction is basically a rearrangement of atoms among different molecules. If the total binding energy of the reacting molecules is less than the total binding energy of the product molecules, the difference appears as heat and the reaction is exothermic. The opposite is true for energy absorbing, endothermic, reactions. Since the atoms are merely rearranged but not destroyed, the total mass of the reactants is the same as the total mass of the products in a chemical reaction. Mass is related to energy through Einstein theory. E equals mc square, where c is the speed of light in vacuum. Law of conservation of linear momentum. Symmetry of laws of nature with respect to translation in space is termed as law of conservation of linear momentum. Example, law of gravitation is same on Earth and Moon even if the acceleration due to gravity at Moon is 1/6 than that at Earth. Law of conservation of angular momentum. Isotropy of space, no intrinsically preferred direction in space, underlies the law of conservation of angular momentum. Thanks for watching.